All right, welcome everyone. So we have looked at square matrices A that have a collection of n linearly independent eigenvectors. And under those conditions, we've shown that A can be diagonalized. And in fact, we know how to construct a matrix P that's going to allow us to diagonalize A so that we can find a similar but diagonal matrix for A. And that allows us to do a lot of computations more efficiently. So the question is there a similar sort of result that we can get with a matrix A that has complex eigenvectors? So here we're just going to restrict ourselves to considering a 2 by 2 case where A is a 2 by 2 matrix. And let's recall some of the facts that we know. So if A has two distinct real eigenvalues, then we know it definitely can be diagonalized because each of those eigenvalues is going to have a basis for an eigenspace, which we know are going to be linearly independent. So we're going to have two linearly independent eigenvectors. A is going to be able to be diagonalized. If A has one repeated real eigenvalue, it can be diagonalized if the corresponding eigenspace has dimension 2. If matrix A has at least one complex eigenvalue, then it is not going to be able to be diagonalized. So remember, we've already seen that if the characteristic equation for A can't be factored into a bunch of linear factors, then it is not diagonalizable. So having complex eigenvalues is an example of when the characteristic equation, which was quadratic, couldn't be factored into two linear real factors. So we're not going to be able to diagonalize these matrices that have complex eigenvectors, but there is going to be a similar result that we can do so that we can find a similar matrix, which is going to be a little bit easier to work with. So let me state that result here, and then we'll use this theorem to summarize the case that we've been looking at so far. So if A is a real 2 by 2 matrix, so all of the entries in A are real, however, the resulting characteristic equation does not have any real roots. So we have complex eigenvalues, and these are going to come in pairs. So we're going to get one that looks like A minus BI, and we're going to get one that looks like A plus BI, where here we're just assuming that this imaginary piece is not zero, or else these would not be complex, they would be real eigenvalues. And let's assume that lambda has a complex eigenvector v, which has some real and some imaginary part to that vector. Then we can find some matrix P, which is going to consist of two columns. It's going to be a 2 by 2 matrix in this case, where the first column we're going to choose to be the real part of the eigenvector v, and the second column is going to be the imaginary part of eigenvector v. And so if I take my matrix A and I multiply on the right by this matrix P and on the left by this matrix, by the inverse of this matrix P, then we're going to wind up with a matrix C where the diagonal entries are going to be the real part of the eigenvalue lambda, and then the off-diagonal entries we get from the imaginary part of the eigenvalue lambda. So in other words, A is going to equal P times this matrix C times P inverse. So let's take a look at what all of these matrices are going to be in the example we've been working with so far. So the example we've been working with, we've had a 2 by 2 matrix A where the first column was 4 minus 1 and the second column was 5, 2. And one eigenvalue of this matrix was lambda was equal to 3 minus 2i. And the other, therefore, was lambda bar was equal to 3 plus 2i. But this eigenvalue, 3 minus 2i, a corresponding basis for its eigenspace, we found that that could be written as v, where v has a real part minus 1, 1, plus I times the imaginary part, which is 2, 0. So that's one such basis for the eigenspace corresponding to lambda is 3 minus 2i. So this tells me that this matrix P, which has two columns, the first being the real part of this vector, and the second being the imaginary part of that vector. So the real part is the -1, 1. That becomes our first column. And then the imaginary part, which is the vector 2, 0, that becomes our second column. And then we can verify what happens when I take this matrix C in this case, right? Remember, the diagonal entries are equal to A, which is 3. And then the off-diagonal entries are equal to, I would take this -2, and that goes in the place right here. And then in the other off-diagonal piece, we changed the sign. So we had a -2 over here, and now that means we have a 2 over here. So you can verify that if I take this matrix P times this matrix C, and then multiply on the right by the inverse of P, that will get back this matrix A that we started with. So here is a similar result where we can show that A is similar to a matrix which has a little bit more symmetry to it than the matrix that we started with.